All right. Hello and welcome to our new Astroparticle seminar. And today I'm very happy to present Nelles from DESY Zeuthen and ECAP in Erlangen. Anna got her PhD at Nijmegen in the Netherlands. Then she was a postdoc at UC Irvine. I think that's the first time I met her in UC Irvine. Then she was a DFG Emineder group leader at Humboldt University in Berlin and at DESY Zeuthen. Now she's a staff scientist at DESY Zeuthen, and she's also faculty at the ECAP at the Erlangen Center for Astroparticle Physics at the University of Erlangen. So Anna has worked on radio detection of particles in general, high energy particles, and in particular of neutrinos above TeV energies for a long time, with an eye on discovering the cosmogenic neutrinos. And she's one of the drivers of the development of the next generation radio detectors in the polar regions, Greenland and in Antarctica. And accordingly, she's been involved in several radio detection experiments. First in Auger, where she was involved in AERA, the engineering radio detection array, and also in the surface detection at some point. And she's also involved in LOFAR for radio detection of cosmic rays. In Ariana, the Antarctic Ross Ice Shelf Antenna Neutrino Array in Antarctica. Now she's involved in RNOG, the Radio Neutrino Observatory in Greenland, and in the radio component of future IceCube Gen 2. So her group produces some of the most updated studies and simulations of the production, propagation, and detection of the radio signals induced by neutrinos at the highest energies in next generation detectors. And today we're happy to have her talk about radio detection of astrophysical neutrinos. So Anna, please take it away.
Thank you, Maurizio, for the nice introduction. It's always somewhat embarrassing hear other people sort of summarize your CV and you go, oh, well, okay, apparently this is the impression I'm making. No, thanks a lot. Yeah, so I'll talk today about sort of, I think, what is the last person who listened to my seminar said, you know, a full tour de force of the world of radio detection of astrophysical neutrinos. It will sort of basically touch upon theoretical aspects, practical aspects, sort of hopefully to give you a more comprehensive picture. Because of course, you know, you heard from Maurizio, I've been doing radio detection my whole life now, but I still distinctly remember this moment after my master's when I sort of looked at different PhD positions where my advisor of my master's degree told me, you consider going into radio detection of air showers? Are you sure? Those are like those crazy people, they can't even agree on what emission mechanism causes this and they fight all the time and they never had a working detector. So are you really sure you want to do this? And I was like, yeah, it sounds fun and exciting to sort of look for something that nobody has ever done before. So I guess, you know, with that argument, I had convinced my advisor. And that's what then, yeah, brought me to Nijmegen. And then in the end to what you see here on the title slide, to Antarctica. I just realized I've taken sort of the fun part out of it. My seminars used to have a whole section about how it is to spend 27 days in one of those tents. So what you see here, the big one is sort of the science tent where we do science. And then those four little ones that you see, those are the mountain tents that we sleep in. So if you are a camping aficionado and you think, you know, you've done it all after 27 days out there all alone in Antarctica, then you finally realize that, you know, all the outdoor camping you've been doing was just a little bit for whiners. Anyway, so should you have any questions, I'm of course happy to answer these. I have a little short break in between sort of for a first half of questions, so then there should be plenty of time. So let me start briefly by the scientific motivation. So why are we doing this? What sort of is the driver behind all of that outdoor camping that I'm doing? So where does it go? So this is one of those, by now, I think almost famous multi-messenger plots that I think Marcus Alers was one of the first to produce one of these, where we put sort of all the high energy messengers together on one figure. So we have the diffuse gamma ray background from Fermi, we have the high energy neutrinos here just depicted by the fluxes measured by IceCube, and we have the ultra high energy cosmic rays as Auger measured them. And sort of the interesting thing is that you can make lots of theoretical arguments that I won't go into detail because I'm just the experimentalist here. But you can sort of, just the fact that all of these are sort of on the same flux scale is kind of tantalizing and indicates that they're all somewhat connected. And I'm particularly interested in this connection between ultra high energy cosmic rays and neutrinos, because no matter how long Auger has been searching, it is completely or relatively unclear where this super high energy tail actually comes from. So particle energies of, orders of magnitude above what human-made accelerators can do. The universe does it, and we don't know how. So you can get two effects, basically. So from these ultra-high energy cosmic rays, you can say, well, in the sources where they're accelerated, you have matter, and in this matter, when you get, let's say, protons accelerated, they'll interact and they'll make neutrinos. So these will be sources of neutrinos, would then immediately equal to sources of ultra-high energy cosmic rays. And all those reddish lines that you see there for neutrino flux predictions are source models, sort of, from AGNs, clusters, blazar, pulsars, all sorts of things. They, of course, all mainly try to explain the IceCube flux, but what you see is they reach very far into the high energy regime. And then you have the three goldenish lines there. Those are neutrino flux predictions that say, if you have those ultra high energy cosmic rays and they interact with photon fields in the galaxy, so let's say the cosmic microwave background or the infrared background and these things, they should react and also form neutrinos. So these are sort of the more diffuse predictions. And also there, for the neutrino flux, you really see they're in this energy regime between sort of 10 PeV and 10 eV or so, where IceCube is just too small to measure something. So if we were to put, like more blue dots here to measure exactly what's going on, we would really help the case of what are the sources of ultra energy cosmic rays, and maybe finally be able to pinpoint this down to explain this neutrino flux and how this goes. So this is sort of the brief scientific motivation of why we're doing this. And now the question is, okay, so we need a detector that can measure in this energy range. And as I said already, IceCube is just limited by its size. IceCube is huge, but it's still too small. So we need something bigger, much bigger to build, that can sort of help the IceCube extend the IceCube energy range. And then we enter radio detection. And I do realize that radio emission of showers is not part of any standard curriculum. I have yet to find sort of the professor who in the astrophysics lecture or astroparticle physics lecture actually covers radio emission. And that is not because it's such a new topic, but I think it's sort of compared to many other emissions is relatively complex. And it has only been sort of 10, 15 years or so that it's actually really settled and defined what it is. And I'm actually I'm a new author of this review of this particle data group. And we're actually just writing up a full comprehensive description of this. So this big review book that everybody who's ever studied particle physics has at home, that doesn't even have a comprehensive review of this in it. So this explains why this is not fully standard. So I'll take a minute to explain this more in detail. So radio emission of showers, you basically can explain it from theoretical electrodynamics, and you need three ingredients. You need a magnetic field that sort of, as it's illustrated here, takes the charged particles in your shower and sorts the negatively charged one to one side and the positively ones to the other side. Oops, sorry, wrong direction. And you need what I call charge imbalance, or also called Iscarian effect, where because the shower is developing in a medium, and the medium has electrons in it, but no positrons in it, for obvious reasons, the shower, when it develops in a medium, the shower front accumulates negative charge. So this negative charge accumulation, it's a particle physics process because you can, kick out the electrons from the medium, but there are no positrons. So then you get a charge separation, and that also leads to radiation. And then finally, what you need an index of refraction in a medium to fully understand what's going on, because you can have this funny situation where one would expect geometrically that if you follow this first arrow in the shower, that's faster than if you go along the shower first and then go to the antenna. But it turns out if you calculate it with the index of refraction in it, this second arrow might actually be faster than the first one. So this makes it a little more complicated to calculate. So how do we know that we need these three ingredients, and sort of how does it even go together? The key evidence is really polarization. So if you have from this first one, the geomagnetic effect, where electrons go to one side and positrons to the other side, it's really an effect of the Lorentz force. And right-hand rule, shower axis, magnetic fields, sort of the direction goes in this here, sort of the result goes in this direction. It means that the induced electric field has the same polarization as function of all the observers. So what you see here is you just think of it as the shower axis being at the center and the origin here. and all those little arrows around it are observers. So it doesn't matter where your observer sits, it will always see the same polarization, a polarization that's induced by the magnetic field and the shower axis. If you think of the Ascarian effect, this is a rotationally symmetric problem because sort of the shower axis, sort of, there are more particles towards the shower axis and fewer to the outside. So if you have a negatively charged shower front, it sort of looks rotationally symmetric. So it should matter where you are with respect to the shower. And that's what you see here, is that all the observers around your shower axis see a polarization that's pointing towards the middle. And if you add this all up now, you can just do vector addition. You see that you get sort of a funny, on one side you get an enhancement, on the other side you get a sort of canceling out of those vectors. And what you see here is sort of measurements we've done with LOFAR. And because LOFAR, you see on this colorful image with the little circles, LOFAR has this funny antenna position. So all the circles are LOFAR antennas. So they're a little oddly for astronomical reasons. So to make it better visible, we put a background map of the signal in the background. So you see whenever the colors match, then simulations and measurement agree. So that works pretty well. But what you see here is on one side of the shower axis, we indeed see this enhancement, and on the other side, we see a depletion. So that's, I think, is just the best illustration of that. You need to have two effects at play that sort of cancel each other out and enhance each other on the other side. You can do this, of course, more in detail, and then you can do a full vector calculation. This is also done here in one of those publications. And what you see is in general, this is an air shower. You have this expected sort of, there's just a sign flip in there that all the polarizations are horizontally. But if you know what you're looking for, you see that on the upper half, things are sort of pointing slightly upwards, and on the lower half, slightly downwards. So just from this polarization picture, you can see that in air shower, the geomagnetic effect is dominant, and the Ascarian effect is sort of a secondary correction. If you go to higher frequencies, so before I showed you 30 to 80 megahertz, now it's 110 and 290 megahertz, you see that the emission really is only strong at the Cherenkov angle. And that has to do with this relativistic compression that I talked about earlier, that you can have that sort of geometrically things arrive faster and slower. So at the Cherenkov angle, that's the definition of the Cherenkov angle, everything arrives at the same time. So you get this enhancement at the Cherenkov angle. And it's mostly seen at higher frequencies. So this is why we go here to the higher frequency measurement from LOFAR. So then you get at the Cherenkov angle, you get this sort of emission that you had from your shower, you get it enhanced because of the coherence criterion that it's met. This is, of course, I've shown you this for air shower, but the same effect happens for showers in ice or in salt even. But then you have to think of it as that you have your Cherenkov angle in air is just a degree. So it's really nice, everything is being forward. But if you do the same thing in ice, you have sort of a 52-degree angle. So this whole thing is super wide and sort of not as clear anymore. So it looks a little bit more of like Cherenkov radiation, but it really is not. And if I had another 2 hours, I'll talk about the differences, but sort of just to keep that in mind, it is coherent radio emission, but it's not Cherenkov radiation. And one thing how to remember this is, I always like this one, if one had the same shower development in vacuum, so the same particle emission, it would still radiate in radio emission. So you don't need the fact that you are in a medium with a different index of refraction than vacuum to make your emission, but you needed to understand it to see sort of how this ring is calculated. In any ways, I think you figured out now this is sort of not totally straightforward how to calculate it. And I think the good news is that we have complex Monte Carlos now that do this for us. But I think the question I always ask myself at the end of the PhD is sort of, we've done all these complex calculations, and it's so much easier to just put particle detectors on the ground. Why are we bothering? Why are we doing this radio detection? And I think sort of, we've done these proof of principle experiments. As I said, when I started my PhD, we didn't even know how this all worked. And we confirmed the mechanisms down to really subtle features. It's really quite impressive that I think now the systematics from the emission model itself are like 2% or so right now. And that's mostly because we can't, we save on computing time because we do air shower thinning. So we've developed lots of data reconstruction methods. We've removed all sorts of, I don't know, I looked at this and it was a huge list of papers. But in my opinion, now this technique is really only useful if it contribute to advancing the astroparticle physics science case. So, you get so entrenched in your topic in your PhD and you just want to squeeze out the last two, details and these and that here. But in the end, we're interested in sort of broader things. We're interested actually in what are the sources of ultra high energy cosmic rays. We're interested in sort of advanced particle physics. And then, taking a step back, you could be interested in air shower physics, in sort of acceleration propagation. And then the two means to get us there are cosmic ray composition and the cosmic ray energy spectrum. So can we, with radio detection of air showers, contribute to cosmic ray energy spectrum and composition? Well, actually we can, because the great thing about radio emission is that it's an excellent energy estimator. So if you ever worked in air shower detectors like Auger or telescope array, they are really good at energy estimation with the fluorescence detectors. However, the fluorescence detectors just require this enormous amount of calibration. You need to know, I don't know, the aerosol quantities, you need to do the temperature, the clouds, and sort of, there's a whole sort of huge analysis and effort going on to calibrate this to get the energy scale right. And then you follow the comparison between telescope array and Auger, and you still see that comparing the two experiments is dominated by their uncertainty on the energy scale. So when you just compare their spectra at face value, you'd say, oh, they don't agree. But then in the end, if you fold all the systematics in from them not knowing the energy scale, they actually do agree. So the great thing about radio is you don't need all of this. You don't need sort of calibration on hadronic interaction models. You don't need atmospheric correction, or very little only. You can calculate from first principles. You calculate from electrodynamics. And as opposed to sort of QFT, there are very little parameters you can tune. So it's just great, it comes out. So what my colleagues found in simulations here is that really less than 5% are in the method. And if you do it then on data, this is basically the energy in radio on the y-axis versus the energy in the Auger surface detector on the x-axis. And you can draw this nice correlation through here, and you see a lot of scatter. And the interesting thing is that the scatter can exclusively be explained by the energy of certainty of the Auger surface detector. So radio, the uncertainty on the radio energy has to be much, much smaller than of the surface detector. And right now, this is, I think it's a relatively old measurement. Oh God, I'm saying this already. Sort of this is more than 5 years old now. So this was still dominated by systematics on the radio side. And as I said, sort of Marvin has shown less than 5% should be possible just in the method. So this would be a great energy estimator. So why is this so cool? You could take it, for example, to actually cross-calibrate arrays, because you have negligible corrections due to the atmosphere. So you could take the same radio array and just, carry it to all of the other arrays, and just to say, look, we measure a couple of air showers together and we figure out what the energy scale is, and we just calculate it. And this is sort of something that Katie Mulray from Brussels is working on. And we've tried this now with LOFAR data. So what you see here in this plot is essentially like before, sort of, the radio energy estimate versus a particle detector estimate. And what's plotted on top of each other is the green curve is the sort of the one that Auger predicts, and the purple one is the one we find at LOFAR. And you see, essentially, you see perfect agreement within the systematic uncertainties. So, and to quantify this, basically the cosmic ray scale that we work at LOFAR over the cosmic ray energy scale we work at Auger is basically 1.06 plus minus 20. And that's basically, that is mostly due to the fact that we still include sort of LOFAR, which is why it's called LoRa, particle detector uncertainty in here. And those are just not particularly great. But I think this is something that for me makes this radio detection of air showers still very compelling, because it might actually help us clearing up this annoying discussion about the energy scale. So what's also in there is that the radio pattern is extremely sensitive to XMax. So for those of you a little more in the field, you know that the distance to XMax is, or XMax itself, so the height of the shower maximum, as you see in the little cartoon here, is a measure for the composition. So if you have a light particle, that's more likely to penetrate deep into the atmosphere. If you have a heavy particle, that's likely to interact further up. And just by geometry, basically our footprint size scales with XMax. So we can get extremely high precision measurements, and LOFAR has sort of first shown this to 17 gram, and we've just, I should clear this up. We submitted this to PRD and it's on the archive already just at the end of last week. we've published this update now for LOFAR composition. And what we see is sort of an interesting slight tension to the Auger fluorescence measurements. So the blue ones are the LOFAR measurements and the little stars are Auger. And funnily, it has agreement with all the other Northern Hemisphere experiments. I cannot think of a reason why the composition of ultra energy cosmic rays should be different Northern to Southern Hemisphere. But we also write it in the paper, we don't know. And within systematic uncertainties, it's actually okay. So annoyingly, it's systematic uncertainties again. But it is intriguing. So if anybody has a good idea, the LOFAR collaboration is very happy to hear it. And especially what we're all waiting for is, of course, an Auger hybrid, RD-FD hybrid study, so we can see that maybe there's some systematics we're just unaware of. So this is one thing I wanted to show you, sort of the global neighborhood of what's coming. I've now shown you results from LOFAR, sort of these little blue ones, and from AERA, the Auger Engineering Radio Array. Of course, we couldn't work with sort of previous experiments like Lopez or Coda Lema that have done so much for our field. And sort of disclaimer, I'm not showing the Auger upgrade that's planning to put surface radio detectors on all surface detectors of Auger. So this is really, it's a lot going on for, something that people thought was just crazy. And one thing sticks out, you see it here, is those red one, that's SKA, the square kilometer array. Of course, a radio interferometer made for radio, sort of radio astronomy, but I'm excited that we're also looking into radio detection with SKA, because if you see LOFA already, this is just basically showing you cartoons. You see LOFA already, you can already see from the color scheme here, this banana-shaped region with the enhancement that I showed you before, you can almost make it up. But we need to do a lot of interpolation and a background map in order to see it. If you do the same thing with SKA, you don't need to interpolate. Basically, this feature, it's the same air shower in both, this just jumps at you. So SKA just has a crazy amount of antennas. It has better frequency coverage. And what we believe is that the radio emission may actually contain information about the whole shower development, not just XMax, but you can see clumpiness, you could see sort of all sorts of things. And we think that this may actually be relevant for both for particle physics and air shower physics. So, we should start working on SKA. So we have all these ideas going on, but it's right now we're still very much in the method development phase. How to actually do this better, because right now we're, as I said, systematics limited, and that's because of the hadronic interaction models. We need them to interpret our data, and it'd be so much nicer to do without it. So, maybe the SKA can help. We're sort of a, high energy focus group, I think, sort of within SKA. So we're working on it. It's still early phases, but this is something to look out for in the future when SKA comes around. So let me now talk a little bit about sort of experiments and why this whole thing has been sort of challenging, let's say, because it's not a new idea, this whole radio emission business. So in the 60s, this Ascarian emission, paper from Ascarian from, I think, 59 or so. Then there was a huge effort from Jelly et al. In sort of in the 60s, they searched for this radio emission. And now basically you see it from the image why this is so hard. So they had a particle physics trigger. Those are the little dots you see here. And then you had radio emission come in. So the particles are faster than the radio emission, so that's good. And they had an oscillator running and a little clock, and they took a picture. And with this amount of data, you had to reconstruct the air showers. And that's just, to me, it's still amazing that they could do it, but it just shows you how limited it is, because they had a very small bandwidth, 40 to 48 megahertz. But you're looking for a super rare signal. And you need to sort of, the polarization, as I said earlier, contains information, the frequency content contains information, and you want to run it on low power, and you want sort of all these things. And if you compare it to like a modern measurement by LOFAR, this is what LOFAR measured, just an air shower pulse, you see all this structure in there and everything you can use. So just our advance in technology, digital, fast, cheap digital electronics have made this possible that we can do radio emission detection now. And to prove somebody wrong who wrote in, I think, some ICRC paper from the 70s, essentially, he wrote, this is just too complicated, that will never work. It's not to say that it's not complicated. So here is, I think, a nice illustration of the experimental challenges. This is a paper we wrote with the Ariana collaboration looking for cosmic rays. And this is 1 year of data, and all the dots you see in here are triggers. So when our experiment said, hey, I saw something. But only the purple points that you see are cosmic rays, and all the other crap is background, because a lot of things make background. You can, look at everything you have on your desk. Probably lots of things of this make radio noise. Everything that switches, everything that just, even walking on snow, crunching the snow, the static discharges you get from that makes detectable radio noise for us. So, we could do a little quiz. You see it down here, those two pulses. One of them is a cosmic ray, the other is not. So self-triggering and actually event identification is the challenge here. And this is also what makes radio emission so complicated. And we fixed this for Ariana with sort of a template correlation, and that worked really, really well. There's lots more to gain, I think, in modern data analysis methods, getting faster, machine learning, all sorts of things. And the site quality is, of course, very important. I think you can talk to everybody at Karlsruhe with the Lopez experiment that was built right on top of Cascade. Don't do that. Photo multipliers are just extremely noisy. So this is sort of why it's actually not so trivial to build one of those experiments. And just for the little quiz, that one is a cosmic ray, the other one is not. I'm not going to ask who got this right now, but from the radio data alone, it's really, really hard to tell just by eye. You need a little bit of extra work in there. So one last slide before we can sort of take a first round of questions. What I really wanted to iterate on is sort of something very fundamental. All showers with an electromagnetic component make a radio signal. So it doesn't matter the particle that induces them. It's a gamma ray, a neutrino, a cosmic ray. As soon as you have an electromagnetic component in your shower, you get a radio signal. The differences are related to the frequency where the emission is coherent. So rule of thumb, small showers, small wavelength. So if you have an air shower, that's sort of the length of orders 10 kilometers, you get very low frequency, sort of 30 to 80 megahertz is the golden band. And if you take a shower in ice, that's mostly like 10 meters. So you all of a sudden, the best frequencies shift to, high megahertz frequencies. Also a difference is the Earth magnetic field is really, really weak. So you need a long shower to see an effect. So essentially the geomagnetic effect is only important for air showers because they are long, they get a long time to develop. However, the density of your medium, i.e. the number of electrons, determines the strength of your Ascarian effect. So where in air showers, the geomagnetic effect is dominant, in ice, the Ascarian effect is dominant. So it's the same mechanisms, but it's just different realizations, sort of different tuning of things. But what I found is that the synergies are really, really nice in reconstructions, but sort of, I think me and Harms Rohrlemmer, we were sort of the first ones to move over from radio detection of air showers to the neutrino community. And I think it's really nice that this is growing together now. So yeah. We can take a break here. Maurizio told me this is something that you do. So if there are questions up to here now, I'm happy to take them.
So I have one question, Anna. So if I understood correctly from one of your slides, the XMax measurements are not limited by systematic errors. So that's a small contribution.
Yes. So this one here. So basically, this axis here, the XMax, is for radio that is not limited by systematics. The problem is, you see it in here, is sort of the translating this into a particle. So the three red lines you see are predictions, for iron, and the green ones are the ones for proton. And the three different ones is just a mean XMax that you get out of three different hadronic interaction models. And you see that the difference between those lines already sort of the difference between experiments. So it depends whether you take, for instance, QGS-JET to interpret your data, whether you get all protons or maybe more intermediate materials. So at least for radio, we're not systematic limited in measuring the XMax, but in interpreting it.
I see. Okay. I see Marcus has a question.
Yes, I have one question about this LOFA plot that you showed. I think this is like
this one, or
then the next one where so basically, yeah, the next one. I think no, this was the one where you had like cosmic ray detections compared to the background, and then you had like one cosmic ray and one non-cosmic ray radio.
Oh, the Ariana one, yeah.
Oh, this was Ariana. Ah, okay,
yeah.
Okay. So I see. So this is Ariana. So you don't have any external triggers here. So this is all done on the fly with the radio amplitudes.
Yes.
Okay.
Yeah.
Thank you.
So this is we're working on this for LOFAR. So it's the same for ERA and LOFAR. We can, in principle, self-trigger. The problem is for LOFAR, it's politically not desirable because they're just very scared that we'll block all their bandwidth and that all the radio astronomers don't get data out. So at LOFAR, it's politically not desirable for us to do it. And at Auger, it's sort of the only thing we'll ever publish are coincident events with SD and FD anyway. So there's no point in developing a self-trigger if you anyway afterwards search for coincidences. So this is why there, you could develop it there, but there was never really pressure to do it. So in Ariana, that's of course different. We don't have particle detectors.
So this the self-triggering is then basically limited by by the capacities to analyze the data on the fly, or are you having these triggers then a very long time after the observations? Do you have to store the data over a long time?
So this depends on how you build your system. So what we're planning for, I'll talk about this later, for RNOG, is that all our stations just trigger and continuously send out data to like the station, and then you can analyze it there, and then you decide to send it south or north or something. So this is much more real time. For Ariana, however, because this is so remotely on the Ross ice shelf, the strategy was for the stations just to record the data. So they write all of this onto SD disks, and then I don't know, once every couple of hours or so, they establish a communication link, which with like a mountain and then to a station. So that needs a lot of power. And during that time, we take data taking off. So you don't want to communicate all the time, but you sort of do it just in certain periods. So this one, Ariana, triggers less often and is less real time than sort of what's planned for future experiments.
Okay, thank you.
I think John has one.
Yeah, hi. May you remember just the last point that you mentioned between the difference between like emission in ice and in air? Like, is it only the strength of the Ascarian effect which is different?
Yes. So it's it's both. It's the Ascarian effect gets stronger in ice, and the geomagnetic effect gets weaker. And in air, the geomagnetic effect gets stronger, and the Ascarian effect gets weaker. So it's those two things. But for the rest, it's essentially identical.
Okay, thank you very much.
All right, I see no other hands, and I think we can go on.
Okay. So to recap, this is what I do now. So I don't do a lot of air showers anymore. I focus on the neutrino detection. So what are we looking for? We're looking for, here it summarizes again, we're looking for this these super short signals. So if you're directly on the Cherenkov cone, these are the ones in blue here from a neutrino, you see a nanosecond scale pulse, really sharp, that is extremely broadband. So this is in megahertz. It has the strongest frequency somewhere at like, what is it here now, 1.3 gigahertz or so. But if you move off the Cherenkov cone, you immediately get into less high frequency. And for instance, this purple one that you see, sort of 4 degrees off the Cherenkov cone, that basically looks like an air shower signal. So what does that look like? So you can, maybe this 3D event viewer that one of my students wrote, you can see this here as a nice illustration. So this blue thing here is the neutrino coming in, it interacts, and then the red cone you see would be the Cherenkov cone. But we also see emission on and off the Cherenkov cone. So what I drawn in here are the orange lines of the ray tracing approximation to what's up here, the station. And you see per antenna, you see 2 rays, because the emission can either travel directly or it travels to the surface, gets reflected at the surface, and comes back down. So in ice, to complicate matters, you don't just have everything nicely forward beamed and easy, but you have to really do ray tracing to see how in this changing index of refraction of ice your signal gets to your antennas. And then unfortunately, ice attenuates the signal too, air does not. So in air, I think the attenuation length is, it does technically, but I think it's like, about something like 1,000 kilometers is the attenuation length, so it's really negligible. In ice, however, you get attenuation length of a kilometer. So for the typical geometry, you have to take that into account. So this is what we're looking for now for the neutrinos. And why is it actually interesting? Well, it is interesting, as I just said, this attenuation length business. despite it being so much shorter in ice than it is in air, it's still huge compared to optical. So IceCube is limited by in its size by putting the sort of the optical modules relatively close to each other, because you have attenuation length of tens of meters or so. A kilometer immediately gets you sort of a factor of 100 more. So you can build your instrument 100 times or even less sparser and still cover the whole area. And of course, it's multi-purpose. So you can do all sorts of things with it. So that the same station will measure the air shower, it will measure the neutrino interacting in the ice, making radio emission, detecting it. And it could even, if you have mountains nearby, detect a neutrino going through the mountain, making a tau coming out, tau making the air shower. You could even detect that. So let's go through this slowly. So as I said, cold polar ice, attenuation length of a kilometer. So one radio station is typically the size of IceCube when you look at effective volume. So that's just crazy, the size you're getting. However, our detection threshold is sort of, you know, don't hit me on this one, 10 PeV or so. So where IceCube stops measuring is where we start being sensitive. And this is not determined by any array size or some other geometry things, but it's determined by the pulse strength that you need in order to get above the thermal noise. So you always have a thermal noise floor in your antenna, and if you need a pulse that is higher than this thermal noise floor, your shower needs to have roughly 10 PeV. But you do need these like hundreds of cubic kilometers to actually obtain enough sensitivity for cosmogenic neutrinos or the ones I talked about earlier. So you need a huge detector, and preferably you'd be in a region where human-based background is not a problem. So self-triggering is easier, event identification and so forth. There were many early experiments, RISE, Ariana. I've worked on Ariana. I've showed you this, but this has sort of basically been the idea. And of course, there's Anita, and no talk without talking about Anita. So the neutrino limits from radio detection of neutrinos are really not competitive below 10 to the 10 GeV, because most of them were proof of concept, reconstruction, performance, all of these things. The one exception is, of course, Anita. And, you know, with everybody, if you say Anita experiment, everybody says, ooh, mystery events. So those behave like cosmic ray signals, but they show a polarization or polarity, what you like best, like a neutrino from deep through Earth. So this is certain implications. So Anita measured cosmic rays before, and the flux measurement also is really nice. But you know, they see sort of these weird events. So if there were truly neutrinos, it would actually mean you see a disagreement between the IceCube limits and Anita. So that's just not reconcilable. And it's also difficult to even reconcile the events that Anita sees with standard model expectation, because at those energies, you simply don't expect a neutrino to make it through the Earth. So the collaboration and many other people have offered sort of all sorts of explanations, the ice background and whatnot. And Anita 4, so the fourth flight of this balloon you see up there, they found again 4 events that were with inconsistent polarity, but they were near the horizon. So there was nothing mysteriously steep about them. So Anita 4 didn't really provide any handles, because there were these funny events, but you know, they could be neutrinos, but you know, they were not enough. And so it's all a little bit of a mess. So that's why I was very happy to hear that Puello has been funded. So Puello is the successor of Anita. So Anita has flown 4 times, and I think that's enough now. There's not much you can expect for this now. And Anita has a much lower energy threshold, which would be really nice, because you know, then you could see where this sort of, it takes over from IceCube at 10 to the 18 electron volts. So that's much lower than Anita. It has a large instantaneous effective volume. So if this thing that they're seeing is some transient events, they should be much better suited to see it. And you know, there's some technical aspects of how they actually made this happen. They use an interferometric trigger, digital filtering, improved pointing, and all sorts of things. So this was selected by NASA just end of last year, and it was scheduled to fly in December 2024. And I'm really looking forward to sort of a time after that where I don't have to say anymore, I don't know what the Anita mystery events are either. I have to say I'm a little skeptical that there are all sorts of new physics. There's more mundane explanation for it. but I also haven't seen a mundane explanation that really knocked it out of the park. So I'm very excited to wait for what Puello has to say about this. So from my perspective, where will radio detection of neutrinos go next? This is Rnog, so the Radio Neutrino Observatory Greenland will hopefully, knock on wood, start construction in 2021. So we planned this array of 35 stations, which will really be the first sort of name-worthy radio array to detect neutrino. We went to Greenland, or we decided to go to Greenland, because it allows for us a faster turnaround. Antarctica, again, next season has been canceled, and Greenland, we're still on go. And it is this sort of a Europe-led experiment at the moment. So it's me and my colleagues from Brussels who are sort of pushing the cart there, and our American colleagues are along for the ride with all the expertise that they bring on board, but it's sort of not a huge NSF project, but it's really so we expect Rnog to have the largest yearly neutrino sensitivity at above 10 PeVs that you've of all the radio arrays. And you can read more at this concept paper that I think, I just got a mail that it's now published with JINST. How does this work? Sort of, you see it here at the little star. It is Summit Station right at the highest point of Greenland in the middle. Well, we get to build this array. It's a NSF station, so the Americans are involved. And all those orange points you see will host one of those stations, and I'll get a little bit further into detail what they do. So this is an Rnog station, and you look at it and you see a lot of detail. So let me walk you through what all of these things do. So the first thing you see the red, yellow, and blue antennas. And those red, yellow, and blue, the red and the blue antennas, I should say. The yellow ones are calibration pulsars. And you see they're distributed in all these different strings, because the deeper you go into the ice, the better your field of view. But also the deeper you go into the ice, the more expensive your detector. So you keep kind of a balance of that you don't go too deep, because then it gets too expensive, and that you sort of cover everything. But in order to get the signal out, it's sort of what we managed to work on. That's like a new thing we're using here. We use RF over fiber to transport our signal out. And sorry, that's where that went. I was like, okay, that's the wrong order. Yeah, so we have the combination of all those two antennas because we need to do a full electric field reconstruction. I talked about polarization earlier, and polarization you can only get if you get the 3D electric field vector. So what you see here as H-pole are antennas that are sensitive to the horizontal polarization of your signal. The V-pole antennas are sensitive to the vertical polarization of the signal. And if you combine this with the fact that you get an arrival direction and the electric field has to be transversely polarized, you have your three measurements of your system in order to get the full electric field. So we combine all of these antennas together and then use RF over fiber to get our signal up in high quality. Then at the surface, we have sort of, those are in Ariana type log periodic dipole antennas to do as what I said earlier, to also detect the cosmic rays, to have a calibration signal, to have a veto and a high fidelity reconstruction. And then we use really deep down this phased array trigger technique that's also used on Puello to get the highest effective volume and most neutrinos out. And then we distribute some antennas around for arrival direction reconstruction and neutrino vertex reconstruction. So these stations are quite complex in their self, and I'm sure they're likely to change. This was the first setup. So what is the science we're going for? I like to phrase it sort of as Rnog is big enough to have a reasonable chance to actually detect it. It's not going to be big enough to knock it out of the park, but it has a reasonable chance to detect the continuation of the IceCube flux. And how you read the top plot is that purple line that you see there. This is, if we don't detect a single neutrino in 5 years, this is the range of the IceCube flux that we can exclude. So you see that if you, I don't know which, I think this is the muon spectrum. If you just draw that through, we can exclude it, that is there. Of course, there are different spectra from IceCube, and unfortunately the more steeper ones we can't exclude, but at least for the flatter ones we can. We do have a somewhat optimistic chance to detect transients events. You see it at the bottom. So some predictions of magnetars and sort of short GRBs are there, but the astronomers among us will notice that you have to assume for the GRBs to be really close in order to see this. However, it has a nice complementary sky coverage. So if we were to build a detector at South Pole, you see it here with the green hashes, and Greenland, that's sort of nicely complementary to in the instantaneous field of view. So this is something that's relatively new, talking about flavors. So the interesting thing about this is not just Rnog, but all radio detectors were sensitive to all 3 neutrino flavors. And what we've been finding is that 20% of all our detections are coming from the interactions of secondaries. So what you know from IceCube, sort of the outgoing muon, the taus, those are the ones we actually get. And this, we never considered this beforehand, because they give you an interesting new event topology. It turns out that muons, yes, you know, they emit Cherenkov radiation, but they also pair produce all the time. So you get along a muon track, all sorts of little showers at those energies that we're talking about. And all those little muon showers that you get, we can use for event topology identification to do flavor tagging. This is really sort of my former postdoc, Daniel, wrote this paper showing that this is actually something we should consider. And Stefan, my new postdoc, is now working on actually figuring out how to do flavor identification. So this is unfortunately work in progress, but I'm very confident that Stefan, well, he just started half a year ago, so he's on it, that he'll in the end will show us how to do flavor physics with radio detection of neutrinos. So one more thing, sort of just to give you an idea, how are we planning to do energy? This is sort of what you need to do is this vertex distance. Just from this cartoon, you know already, if you need to scale from the distance that your neutrino is there with the attenuation length and sort of everything, you need to know where your vertex is, and then you can figure out what the energy is. So you need this vertex distance as ingredients. You need the signal fluence, it should be not fluency, that scales potentially energy, and the neutrino inelasticity. So Christoph Welling, my PhD student, is working on this, and you see this here, sort of a 3D interferometer of pinpointing down the neutrino vertex. This seems to work really, really well. So for energy resolution, I'm expecting radio detection to be dominated by what it says here, this neutrino inelasticity, so the unknown fraction of energy that actually went into the shower, something that's irreducible, that's just stochastically. So this is something will, again, like in air showers, will be really good with radio. And then for the arrival direction, maybe we won't be as good. And this is due to the fact that in our signal, we have timing. So, but that timing only tells us where the vertex was. So if you look at this here, sort of the timing, the arrival direction timing tells you where the vertex was, but it doesn't tell you sort of around the Cherenkov cone, you have a discrepancy or an ambiguity. So you could rotate basically your neutrino axis around the Cherenkov cone and it will still count. So you need frequency content and polarization to resolve this. And this is a nice image by my other grad student, by Ilse, showing how this will work. If you only know the radio signal arrival direction, you get this sort of huge banana region on the sky. If you know the viewing angle, which is the viewing angle to the Cherenkov cone, so the frequency content, this huge banana shrinks. So then you get this orange thing. And if you add polarization to the game, so the full electric field reconstruction, you end up with this little blue spot here to reconstruct your arrival direction. So this is work in progress. It's looking really great, but it turns out we're sort of the first ones looking into detail because no experiment ever had a detection. So why would you even consider the arrival direction? So we're of course working towards multi-messenger astronomy with ultra high energy neutrinos. And for that, we would like to tell the community, look, we found an ultra energy neutrino and it's from there, rather than we found one and you go figure out where it's from. So what will happen next? And this is what I would like to close with is, of course, you have to think ahead. Rnog will happen this or next year, and then we'll measure for 10 years. But what will happen after? So something that the community as a whole, the neutrino community, is working on is IceCube Gen 2. And this is sort of one of the PR images we've been making at DESY. Gen 2 is just going to be huge. And the main thing will be an extension of the optical array. This is where 80% of the money goes and 80% of the excitement goes. But of course, there's radio. And I think I need to make one point because we're having terrible PR at this. Gen 2 will have two things with radio, and people tend to get this confused. So there'll be something that's now called IceTop. So the surface array that will include radio antennas for air showers. So this is at the surface above the optical array, and that's exclusively for cosmic rays. So you see it here, it will have scintillators and a radio antenna. So this is something where radio comes in, but this is not sort of what I'm talking about. This is exclusively for cosmic rays. This thing here, the radio array station, are the ones that go all the way to the horizon in this artist depiction. And that is much larger than the optical footprint because we need such a huge detector, and is dedicated for neutrinos. But we also happen to detect air showers just because they make the same signal. So that's, I think, where the confusion comes in. So I think I'm making the point that what I'm working on is sort of the radio array for neutrinos. So the nice thing now with Gen 2 is it will span this entire energy range. And radio is, I think, from like 10 to 8 GeV or so, the dominant part of measuring this energy spectrum. So we have this huge white paper, and I'm sure everybody is aware of, where this plot is also from, for a baseline design for IceCube Gen 2. And it comes in lots of phases. Right now, the IceCube upgrade is going on, which is sort of an infill to IceCube. Then there's the optical array that will come, and what's depicted here, this huge radio array. So we were scheduled to start deployment for the IceCube upgrade next season, but COVID delays are really likely. So there are plans to deploy a fraction of Gen 2 already as something like a Gen 2 phase 2. So the upgrade is Gen 2 phase 1, and then there may be a Gen 2 phase 2. And then at some point in the future, there will be a full Gen 2. So, you know, that's just to warn you, if things sort of look modular, this is really what's intended. So for the radio array, we're currently in this review phase, and so this is the one with the purple stations, is the one that's in the IceCube Gen 2 white paper. The one that we've just put forward is something that has been reviewed. So the design of this array, what it will actually look like, we're a little bit behind the optical component, so we're still optimizing this. We do have a target sensitivity that's sort of close to 10 to the minus 10 on this E² plot. And we hope that we'll be able to present the full design and the sensitivity in fall 2021. Those of you ever involved in project management, PDR is a preliminary design review. This is where you have to be ready and actually know what you're building. So I really like the sentence, and this is what I want to end with, is sort of the IceCube Gen 2 will play this essential role in shaping the new era of multi-messenger astronomy, fundamentally advancing our knowledge of the high energy universe. And this is really sort of the ultimate goal. But this is a huge project. It takes a lot of sort of inertia to move forward. So on the meantime, I'll be concentrating on Rnog. And so these are kind of my conclusions, just a brief overview that air showers have been great. They've established that the radio technique works, and we've shown that we can do ultra high accuracy measurements. SKA will do even better. But right now I'll focus on, I'm focusing on the radio detection of neutrinos, because this is really the only cost-effective way right now to build a ultra energy telescope. Our technology has been matured. We're looking very much forward to Rnog in Greenland this summer. And then in the future, IceCube Gen 2 is on the horizon. And sort of on a personal note, if we don't detect ultra high energy neutrinos with IceCube Gen 2, we might as well close the field. There's no point in going bigger, because then the flux is so low that just means that sort of our whole idea of multi-messenger astronomy with cosmic rays, that will, you know, that's just going to be so hard. So we probably shouldn't try. So I'm taking the optimistic route and saying we'll just discover ultra energy neutrinos with Gen 2. Thank you.
Thank you very much, Hannah. I'm also on the optimistic side. Is there any question right now for Hannah? Oh, Marcus has one. Okay, go ahead, Marcus.
Yeah, thanks, Anna, for this nice overview. Can you go back to slide 26? This was, you talked about the angular resolution with
that one.
And so that's very impressive. Are you saying that this can be achieved by just one antenna, so just one station, or?
Yes. All the reconstructions at the moment are with one station. So this is because typically, well, in order to get so large, 80% of our events are only going to be detected, depends a bit on energy, but sort of roughly 80% of the events are just going to be in one single station only. So with a single station, we have to make arrival direction work. Of course, if you, I don't have that plot, that'd be nice. We have a nice plot. So if you have it in two stations, it immediately gets easier because instead of one of those rings, you have 2 rings, and then the intersection of those rings helps you immediately. But this is what we can do with one single station.
So for the RNOG layout in Greenland, you also put the distance between your stations so wide that you're never going to see neutrinos in 2 stations, right? So you always try to maximize your...
Yeah, it's sort of a funny optimization game between you want the most effective volume and you don't want to have logistics cost explodes. So I think we have I also for Rnog, so these are Rnog simulations, I should say. There's I think like a 15% chance or so that we see coincidences, but yeah, it's more likely that we see it just in one station.
So that statement about the coincidences in multiple stations, that's energy dependent as well, right?
Yeah.
Yeah, and so out of the 15% of events that you see in multiple stations, let's say, what is the energy threshold for that to happen?
So it basically is just a continuously upgoing function, because the signal amplitude scales linearly with energy. So if you can, if you go a decade up in energy, your signal is a decade stronger, a factor of 10 stronger. So you get further away, so you have better chances. So I think the last simulations I've seen, let me get this right, they had sort of at 10 to the 18, a 10% chance of coincidences. And at 10 to the 20, I think it went up to like 40 or 50%. But then most flux models sort of see that sort of 10 to the 18 is your sweet spot. So there, I think we optimized it as such, the spacing, that you should have a coincidence rate of something around 10, 15% at 10 to the 18.
That's after weighting with the flux.
No, that's no flux, but you have to weight it in your head with flux.
Okay, I see.
So of all the 10 to the 18 neutrinos in our simulations, 10% are seen in 2 stations.
Okay.
So, yeah.
So since I'm asking, maybe Marcus asked about the angular resolution, I can ask about the energy resolution. Do you have like a number for that? Like what should we expect for the resolution of the reconstructed neutrino energy, let's say? Not necessarily the shower energy, but the neutrino energy. So
that's essentially your inelasticity uncertainty, and that's a factor of 2. So I would think the shower energy. So the shower energy we can do to like 15% or so. So, and then you know the shower energy to 15%, but you don't know how much, when to do the shower. So that's your dominating uncertainty, factor of 2.
Okay. Well, still comparable, at least in some energy range, to what IceCube sees now in optical, right?
Yeah, I mean, it's the same uncertainty for IceCube. IceCube sees a big cascade. They can tell the energy of the cascade really well, but they still have sort of the dominating uncertainty of how much energy actually went into the cascade.
Right. But
I think it's slightly different as a function of energy again. So this is why just factor of 2 roughly, but it's sort of, it's the similar idea that with the showers, it's relatively easy to tell the good shower energy, but yeah, if you don't see the lepton, then it's hard.
I think Marcus has another question there.
Yeah, also on energy. So you mentioned this new mission, Puello, and you said that it has an energy threshold which is a factor 10 times lower than Anita. Can you say why this is? Do they use a different technique or?
So if you compare this picture of Puello with that picture of Anita, it's just way more antennas. So they use instead, so what you do in radio is you sum up signals from different antennas, and your signal to noise ratio goes with 1 over the numbers of the square root of antennas. So basically, if you have 16 antennas, you get an improvement of 4 in signal to noise. If you have 64 antennas, you get almost a factor of 10. So this is just, Anita uses many more antennas, Puello uses many more antennas, and then you do some sort of some digital, there's a lot of digital processing going on in Puello. So where you use improved pointing resolution, you have this trigger there, they optimize the bandwidth. So it's a lot of tweaking going on to reach this. Because all our experiments are determined, it's quite interesting, is that we're all determined by our trigger threshold. So can we get the neutrino in the data? And then the next step is, can we find the neutrino that we have in the data? But the better our trigger is, that is what determines our energy threshold. And for that, you have to do all those phased array gymnastics.
All right. We have time for one final question.
Actually, if I may, it's a logistics, so a more practical question for Greenland. What did you decide now for the power supply of your stations? How is this organized?
So right now, in the first iteration, there'll just be solar panels. So we'll have, unfortunately, we won't be running in the winter. So we just have solar panels and big batteries. So I think we have what do we calculate, an uptime of 60%. So we'll be up all summer, and then it will sort of die out in the winter. But the colleagues from Uppsala, they're working on wind turbines, and the wind turbines are also under discussion for South Pole. And maybe this season, but probably not likely, but probably next season, we'll bring a couple of these Uppsala turbines to Greenland to test them out. Because wind turbines, so funny side note, wind turbines are the most terrible background noise for us. So the typical wind turbine basically spoils your experiment to death. So you need to have a sort of a very dedicated development to have them be radio quiet. And at the same time, they need to survive polar winds, temperatures to down to -50. So it's like from a wind turbine perspective, the dumbest possible idea that we have. But yeah, this is what the colleagues in Uppsala and Sweden are developing. And I'm pretty confident that they can pull it off.
Okay, thank you. Very interesting.
Thank you, Anna. This was super interesting. I'm sure people also enjoyed it as much as I did. So thanks. And everybody, thank you for being here. And we'll see each other in a couple of